Good morning. Let us start off by recapitulating the things that we had learned in the last class. So, if we have an electron accelerating in the direction A, direction of this vector shown over here, then in the last class we learned that in addition to the electric field which falls as 1 by r square, this electron, this charged particle will also produce an electric field component which falls as 1 by r. And I had told you that it is this part of the electric field that falls as 1 by r which is responsible for electromagnetic waves, electromagnetic radiation. So, if you ask the question, what is this radiation electric field? What is the electric field due to this electron at the point over here? The electric field at this point will be so, the way to calculate the electric field at this point is that you should take the component of the acceleration perpendicular to the line of sight from the point where you wish to calculate the electric field to the charge. So, this is the line of sight from the point where we wish to calculate the electric field to the charge. We have to take the component of the electric field perpendicular to this, which is what the dashed line over here shows. So, the dashed line is the direction perpendicular to the line of sight. The component of the electric acceleration in this direction is what causes the electric field over here, and the electric field is given by the expression over here. So, it is minus q, where q is the charge, the value of the charge, divided by 4 pi epsilon naught c square r. R is the distance from the point where we wish to calculate the electric field to the charge, this into the acceleration of the charge at the retarded time. The retarded time is in the past. So, if I wish to calculate the electric field at a time t at this point, I have to look at the acceleration at a time t minus r by c. The term minus r by c takes into account the fact that the signal takes a finite time to propagate from here to here. The signal travels at the speed c, the speed of light, and it takes a time r by c to propagate from here to here. T minus r by c is called the retarded time, a is the retarded acceleration. So, we have to use the acceleration of the charged particle not at the time t, but at a later time t minus r by c. We have to take the component of the acceleration perpendicular to the line of sight, which is what gives rise to this factor of sin theta. So, the particle, the charged particle over here, if it accelerates, produce the electric field given by this expression. The key point is that the electric field falls as 1 by r, and it is proportional. The electric field is in the direction perpendicular to the line of sight, and it is proportional to the component of the acceleration in the direction perpendicular to the line of sight. So, this was the first thing that I told you. The second thing, then we moved on to a particular situation where we can apply this, and we were discussing the electric dipole oscillator. This is a device of considerable technological importance. So, we have two metal wires A and B which are aligned like this, and these two metal wires are connected to a voltage generator which produces an oscillating voltage at these two ends of these wires. Now, if I have a positive voltage here and a negative voltage here, so the bottom of A is given a positive voltage, the bottom of B is given a negative voltage, then there will be an excess of positive charge at this tip of A, and there will be an excess of negative charge at the tip of B. These charges, the negative charge here and the positive charge here, will reverse. So, there will be a positive charge here and negative charge here when the voltage is reversed. So, if I have a positive voltage here, negative voltage here, and a positive voltage here, these charges will get reversed. So, as the voltage oscillates, the charges rush back from A to B. So, we have electrons rushing up and down from A to B and back and forth. So, you can think of it as electrons moving up and down this a single wire, electrons accelerating up and down. These electrons that accelerate up and down will produce electric fields which fall off as 1 by r. If I am sufficiently far away, you will see an electric field component which falls off as 1 by r. This is the dominant thing which you will see if you are far away. And so, we can apply the expression for the acceleration which I just showed you if you are sufficiently far away, and if the time it takes for the electrons to go from here to here and then come back, if this time period is considerably larger than the time period that light takes to cross this, you can think of it, you can think of this whole device as an oscillating electric dipole. So, this is called the electric dipole oscillator. So, when you are quite far away at a distance which is much larger than the length of this, and when the oscillations here are quite slow, you can think of this as an oscillating electric dipole, and I shall go into a little more detail of this shortly later. Now, this kind of an oscillating electric dipole has considerable technological applications. So, much of the radio receivers, radio transmitters, the antennas used over there are electric dipole oscillators. For example, your TV, you might have seen the TV antennas, they are a collection of electric dipole oscillators. They look like an electric dipole oscillator, which is essentially a long metal rod which is cut in the middle and has two leads connected to a voltage source or possibly to a detector. So, let me now consider the nature of this dipole radiation. So, we have a dipole over here, we have this metal rod AB which I just showed you over here, and we have a signal voltage source connected to it. So, this is the generator of the electromagnetic radiation. The electrons accelerate up and down, and these accelerating electrons produce electric fields elsewhere. So, this is a common situation where I wish to transmit some kind of an electromagnetic radiation. I have a dipole oscillator and I have connected a voltage source. The voltage source is the signal which I wish to transmit. So, the voltage source is driving my electrons up and down these two metal rods, and this gives rise to electric fields elsewhere. Now, the question is, then I now wish to study the electric field pattern. So, let us consider a situation where I have a detector located elsewhere. So, this is what this picture shows us. I have a source, the generator over here, and I have a detector located a large distance away from this. So, there is a detector located over here. The detector also is a dipole. So, we have a dipole here and a dipole here. The difference between the dipole here, which is the detector, and the dipole which is the generator, is that the dipole over here, which is the detector, is connected to a voltage detector, could be an oscilloscope. So, if the electric field produced by the generator, when it falls on a dipole located over here D, when the electric field from the generator falls on this, if the electric field is aligned with the dipole, it will produce a voltage across the dipole, and this will cause a current to flow in this dipole. So, if you connect a voltage detector, then it will measure a voltage across the dipole. So, you could connect an oscilloscope and you could measure the voltage across the dipole. So, you can think of this dipole as, you can think of our radio antennas or TV antennas as being some kind of a typical dipole. So, I can use a dipole to measure the electric field produced by this generator, which is also a dipole. So, let us consider the situation where I have a dipole located, let us say to start with over here, and the dipole is aligned in the same direction as the dipole which is generating the signal. So, the detector dipole is aligned in the same direction as the dipole which is generating the signal. Now, the electron which is generating the signal is rushing up and down this dipole, the generator. So, let us ask the question, what kind of an electric field will be produced over here? So, let us go back to our expression for the electric field. The electric field, I told you at this point, if the electron is accelerating over here, the electric field here will be parallel to the component of the acceleration perpendicular to the line of sight. So, this is the point where I wish to calculate the electric field over here, this is the point where I wish to calculate the electric field. The line of sight from here to here is in this direction. So, the component of the acceleration perpendicular to the line of sight is this direction. So, the electric field here is basically parallel to this. So, it is going to oscillate up and down, the electric field is going to oscillate up and down over here, and it is going to produce a voltage in this dipole which you can measure. Now, let us consider another situation where I have moved the dipole on a circle. So, think of the dipole as being attached to this generator through a rod or something like that. I move it around, maintaining the same distance, I move it to a different position shown over here. Now, if I keep my dipole over here and I keep it aligned like this, then the electric field, then let us ask the question, what is the direction, what is the electric field here like? So, you have to take the line of sight from this point to the generator. This line over here shows us the line of sight from the point where I wish to calculate the electric field to the electron that is oscillating up and down. You have to take the component of the acceleration perpendicular to the line of sight. So, you have to take the component perpendicular to this. So, the component perpendicular to this line of sight is going to go down by a factor of sin theta, and the electric field here is going to be parallel to the component of the acceleration which is projected perpendicular to the line of sight. So, it is going to be along the tangent to the line of sight, which is the way the dipole is oriented. Now, let us again consider another position for the detector. So, if I move the detector all the way over here, where it is directly overhead with the dipole, let us repeat the same exercise. The line of sight from the position where I wish to calculate the electric field to the dipole is this. The particle, the electron, is accelerating this way. It has no component, the acceleration has no component perpendicular to the line of sight. So, the electric field produced over here is 0. So, the electric field is maximum when at this point it falls as sin theta as I move further up, as theta is varied, is as theta. So, theta, when theta is 90, sin theta has a maximum value. As theta is decreased, the value of the electric field falls and it is 0 over here. The direction of the electric field at this point is in this direction. It is the tangent to the radius. So, it is a tangent to the line of sight, which is in this case the radius. So, the electric field is perpendicular to the radius, which is the tangent. So, at this point the electric field is in this direction. At this point the electric field will be in this direction. At this point the electric field is 0, but this would be the direction, it would be normal to the line of sight, but it has a magnitude 0. If I move a slight distance away, it will be the tangent. So, the electric field that is produced is perpendicular to the line of sight. This is a point which is important. Another point which is important is, if I put the dipole, instead of putting the dipole in this direction, if I were to put the dipole in the direction which is perpendicular to the electric field. So, if I put the dipole like this and the electric field oscillates this way. So, I have a dipole in this direction and the electric field oscillates like this, then this electric field will not produce any voltage difference across this dipole, and this dipole, this detector, will not be able to detect this electric field. Okay, so, this is a point which we should bear in mind. If the detector dipole is perpendicular, so if the metal wire AB which I am using to detect the electric field is perpendicular to the direction of the electric field, it will not experience any voltage difference and there will be no signal picked up here. Signal will be picked up only if the dipole is aligned. So, if the dipole which I am using to detect the electric field is aligned like this in the same direction, it is only then that there will be a voltage difference produced across this and there will be a signal picked up. So, coming back to this picture over here, if I were to put a dipole in the perpendicular direction here, I would get nothing. The dipole here is aligned with the electric field, so I get a signal. So, this essentially summarizes the direction dependence of the signal of the electric field produced by the dipole oscillator. Now, we are going to concentrate on a situation where the signal that I am feeding in, so the signal that I am feeding in to the dipole oscillator, we are going to assume that the signal is a cosine, is doing, so the signal which I am feeding into the dipole oscillator, the voltage generator, is producing a sinusoidal voltage pattern. So, if the voltage generator produces a sinusoidal voltage pattern, the electrons are also going to rush back and forth, and the motion of the electron between those two wires A and B, across the two wires, up and down the two wires, is going to be sinusoidal. So, we are going to focus for the rest of this talk, we are going to focus on this particular of today's lecture, we are going to focus on this particular situation. And in this situation where the voltage oscillates as a sinusoidal, we can write down the displacement of the electron up and down this dipole oscillator. Y, the dipole oscillator here is aligned with the y axis, and the motion of the electrons as they move up and down this, we can model, we can write as y, the displacement in this direction, charged particle moving up and down. The displacement in this direction is y t equal to y naught, which is the amplitude of the displacement, into cos omega t. So, let me just remind you of the situation again. We have this kind of an electric dipole oscillator. The two metal rods A and B are aligned with the x axis, with the y axis, and we have applied an oscillating voltage source which is oscillating in a sinusoidal fashion, cos omega t. So, the electrons are also going to go up and down in a sinusoidal fashion, and we express the motion of the electrons up and down that dipole oscillator as y naught cos omega t. The electrons move back and forth along the y axis. Now, we want to calculate the electric field pattern at different points. So, the electric field pattern at any arbitrary position distance r away from the dipole can be calculated in using this expression. So, the electric field at a time t, a distance r away, is minus q by 4 pi epsilon naught c square r into the acceleration at a retarded time t minus r by c into sine theta, where sine theta is the angle between the point where I wish to calculate the electric field and the direction of the dipole. So, in this case it is the angle with respect to the y axis. So, this is the expression for the electric field in terms of the acceleration, and in this case the particle, the displacement of the particle is sinusoidal. So, it is y naught cos omega t. This is the displacement. I have to differentiate this twice to calculate the acceleration. If I differentiate this twice, I pick up a minus sign and a factor of omega square outside. So, putting this into the expression for the acceleration, we get this expression for the electric field here. It is q into omega square into y naught by 4 pi epsilon naught c square r into cos omega t minus r c. So, this is the cosine at a retarded time t minus r c into sine theta. So, this is the electric field. This gives us the electric field at the point where we wish to calculate it, and this can be applied to any at a large distance r in any arbitrary direction theta. Now, it is convenient to think of this whole thing. So, we have the whole thing is that we have an electron, we have this these two things. So, we can effectively think of it as one. We have single we have some charge q which is rushing back and forth up and down this dipole. Now, it is convenient for certain purposes to think of it as two charges, one q by 2 and another minus q by 2, and the charge q by 2 is doing this oscillation y t which I just wrote down, and the charge minus q by 2 is doing exactly the opposite oscillation minus yt. So, a single charge moving up and down I can think of as two charges, one of magnitude q by 2, the other also of magnitude q by 2 with the opposite sign doing exactly opposite oscillations. Now, the point is that if I replace a charge q with minus q and replace the acceleration a with minus a, such a change does not change the electric field. So, if I change the sign of the charge and the sign of the acceleration both, the electric field is not changed. So, we are essentially using this property. So, I am replacing one single charge q moving up and down with y of t by two charges, one q by 2 moving with yt, another minus q by 2 moving exactly opposite minus yt. So, the both of them produce exactly the same electric field, and the sum of these two electric fields is exactly the same as the electric field, the radiation pattern of the part of the electric field produced by this. Now, if I have a charge q by 2, so I have a charge q by 2 and it is at a displacement y, and I have another charge minus q by 2 at a displacement minus y. This is a dipole with a dipole moment d. This d is the charge into the distance. So, the charge is q by 2, the distance is 2y. So, this dipole moment is q into y as a function of t. So, this single charge so, as far as the radiation pattern is concerned, the 1 by r component of the electric field is concerned, a single charge moving up and down and the displacement being y of t, I can think of as two opposite charges of half the magnitude moving up and down, and the one of them moving up and the other one moving down by the same amount, and this can be thought of. So, the single charge moving up and down can also be thought of as a dipole which is doing exactly the same kind of oscillation. So, the single charge is moving as yt equal to y0 cos omega t, and we can think of this as also being equivalent to a dipole dt, which is q y naught cos omega t, which I can write as d0 cos omega t. So, which is what is given. So, what I have shown you is that a single charge moving up and down this I can think of as a dipole which is oscillating as an oscillating dipole. So, the dipole moment, the magnitude of the dipole moment is d naught, which is equal to q into y naught into cos and the whole thing oscillates. So, it is d naught into cos omega t, and we can now write the expression for the electric field over here, which we had. The expression for the electric field can also be written in terms of the second derivative of the dipole moment. So, when we have an oscillating dipole, it produces a radiation electric field pattern which falls as 1 by r, and the radiation electric field pattern is given by this particular expression over here. So, the accelerating charge moving up and down you can also think of as an oscillating dipole, as an oscillating electric dipole, and the expression for the electric field you can interpret in terms of an oscillating dipole. So, what we see here is that if I have a dipole, an electric dipole, positive and negative charge, which is oscillating, it could be set into oscillations in a variety of ways. So, I could have real physical oscillations of a dipole, or I could have a positive and negative charge moving up and down. I could have a dipole which is rotating. All of these situations give you an oscillating dipole, and there are a large variety of other situations also. All of these can be thought of as an oscillating dipole, and the electric field pattern produced by this is given by the expression over here. Another convenient way, and another convenient way of expressing the electric field, of the same electric field, is in terms of the current. So, this oscillating dipole let me okay, is in terms of the current. So, the if when I apply a positive voltage to one of these bits A and a negative voltage to B, and then if the voltage is reversed, there will be charges rushing from A to B, and then when the voltage is reversed again, charges will rush back and charges keep on moving back and forth. Now, when charges move, you have a current. So, the current is the rate of change of the charge. The current is the rate at which charge flows. So, it is the rate of change of the charge at the two tips. And the dipole, the rate of change of the dipole, the second derivative of the dipole over here in this expression, you have the second derivative of the dipole. So, the second derivative of the dipole moment is the first derivative. So, you have the dipole is the distance, the separation into the rate at which the charge changes is the displacement of the charge. So, the second derivative of the dipole moment you can write in terms of this. So, the L into I dot, the rate of change of the charge, the rate of change of the current. Okay. And if I have a current which is minus I sin omega t, then the rate of change, the second derivative of the dipole moment is going to be minus L into I into omega cos omega t. So, we can also write the electric field in terms of the current. The I here is the amplitude of the current, and this is the expression for the electric field in terms of the current. So, what we have done is we have written the expression for the electric field in this situation in terms of the dipole moment and also in terms of the current. So, all of these expressions have their utility depending on the situation that you are analyzing. A point which I should make here is that if you look at the expression for the electric field in terms of the dipole moment or in terms of the acceleration, then the electric field depends on omega squared. So, if you double the angular frequency, the electric field will go up 4 times, and this is true if you maintain the amplitude of the displacement fixed or if you maintain the amplitude of the dipole moment fixed and double the angular frequency. But if you maintain the amplitude of the current fixed and double the angular frequency, then the omega dependence, note that the omega dependence is different and the electric field will only go up twice. Okay. So, this is a point which needs to be borne in mind, that the omega dependence depends on the variable in terms of which you are expressing the electric field, and it will have a omega or omega square dependence depending on the variable in terms of which you are writing the electric field. Now, let us go back to the situation which we were considering. So, we were considering a situation where I have a dipole oscillating along the y axis and we would like to calculate the electric field pattern at different positions. Different positions means different value of theta and different distance r. And we digressed a little, we took a little detour where we wrote down the electric field in terms of different variables, the rate of change of dipole moment, the rate of change of the current. But let us now come back to a study of the electric field. So, this is the dipole which is oscillating, and let us calculate the electric field at different points along the x axis first. So, to simplify matters, let us restrict our attention to points along the x axis. So, the expression for the electric field at different points along the x axis is this. So, we have the expression for the electric field and we have replaced the distance r with x, and we also have this simplification that along the, when you wish to calculate the electric field along the x axis, you have to take the component of the acceleration in the direction normal to the x axis. In this case, the electrons, the charged particles, accelerate along the y axis, the dipole is aligned with the y axis. So, the charged particles accelerate along the y axis. If I take the component of this acceleration in the direction perpendicular to the x axis, it is still along the y axis, there is no change. The electric field will be parallel to this component perpendicular to the x axis. So, the electric field will be along the y direction. You will only have a y component of the electric field, which is what I have written here. So, you are going to have an electric field along the x axis, you are going to have an electric field only along the y direction, and the magnitude of the electric field is given by this. It has only the y component, and at a distance x away, you will, this is the magnitude of the electric field. So, the point to note is that it will depend on the acceleration of the charges at a retarded time. The retarded time is t minus x by c, and there is a factor of omega which is there for both of these. So, this takes into account the retardation of the retardation which has to be put in. Now, we shall consider a situation. So, let me now explain to you the situation which we shall consider. We shall be looking at a situation where the dipole is located at a large distance from the point where I wish to calculate the electric field. So, we could take, for example, the point where I wish to calculate the electric field is located at a large distance, say 1 kilometer away from the dipole, and we now move from a point which is 1 kilometer away, we move to a point which is 1 meter away from this. So, this figure is not to scale, you should bear in mind. So, I wish to calculate the variation in the electric field when I move from a point which is 1 kilometer away to a point which is 1 kilometer and 1 meter away. So, the change in the x is 1 meter, and the distance was 1 kilometer to start with. So, you see that the fractional change in the distance is very small, it is 1 by 1000, which is equal to 10 to the power minus 3. So, it is a 0.1% change in x. So, if I move 1 meter from 1 kilometer to 1 kilometer plus 1 meter, there is a 0.1% change in x. Now, let us look at the expression for the electric field and ask the question, how will the electric field vary if I change x by this small amount? So, if I change x by this small amount, the term outside over here is going to change by only 0.1%, and I can think of this term as being roughly constant. The change in x is only 0.1%. So, this term here is also going to change by only 0.1%. But look at this term, the cosine term. If x changes by 0.1%, it is not guaranteed that the change in this term is going to be small. There could be a very large change in this term over here, and the magnitude of this change is going to depend on the value of omega by c. Now, if omega by c is very large, then a small change in x will cause a large change in the phase. So, it will cause a large change in the argument of this cos term, and this change in the argument of the cos term may cause a significant oscillation. See, cosine is oscillating, and a small change in x may cause a considerable oscillation in this cosine term if omega by c is a large number. So, let us consider the situation where we can ignore the change in x in the first term, but we have to take into account the change in x for the term inside this cosine. So, I can think of this as a constant, but I cannot think of this x as a constant. So, if I make this assumptions, if I work in this regime, we can write down the expression for E, the y component which has only a y component. So, the electric field which has only a y component, the expression for that as I vary x and as a function of time is a constant into cos omega t minus kx, where I have used k to denote omega by c. So, I have used k to denote this coefficient omega by c which multiplies x. So, the point to note is that the expression for the electric field if I vary x by a small amount at a large distance from the dipole oscillator, is just the expression for the sinusoidal plane wave which we had studied earlier. So, this is the expression for the sinusoidal plane wave which we had studied earlier. So, what does it tell us? It tells us that if we give a sinusoidal voltage to this dipole oscillator, far away it produces an electric field pattern, and at a fixed time this electric field pattern is sinusoidal, and as time varies the whole sinusoidal electric field pattern will move forward. The electric field is only along the y axis and it has a sinusoidal pattern like this. As time increases, this whole thing will move forward, it will behave like a sinusoidal plane wave. So, this oscillating dipole produces a sinusoidal plane wave at a large distance from the dipole. So, what we see here is that if I have a sinusoidal, if I have a dipole oscillating like this and it is doing sinusoidal oscillations, it will produce a sinusoidal plane wave at a large distance. So, if I go a large distance away from this oscillator, the electric field pattern produced by this will be a sinusoidal plane wave. The electric field pattern at a fixed time will look like the sinusoidal pattern shown over here, and this whole pattern will move forward in time, as we have studied in the lecture on sinusoidal plane waves. So, coming back to our expression for the electric field, you can write it in this form omega t minus k x, where we have identified the wave number k with omega by c. This is a sinusoidal plane wave which propagates along the plus x direction. Now, let us ask the question, what is the wave number? The wave number here is omega by c. Now, once you know the wave number and the angular frequency, you can calculate the phase velocity, and the phase velocity is omega divided by k. So, omega divided by k gives us c. So, you find that the electromagnetic wave, in this situation the electromagnetic wave has a phase velocity which is the speed of light. So, the dipole oscillator over here, if fed with a sinusoidal voltage, produces a sinusoidal plane wave at a large distance. So, over here the electric field pattern produced by this is a sinusoidal plane wave which keeps on propagating outwards. And you could express this in the complex notation. So, E tilde y as a function of x and t is E tilde e to the power I k omega t minus k x. This complex amplitude has both the magnitude and the phase of the electric field. Coming back to our picture, we have the dipole oscillating like this, and if we ask the question, what is the electric field at some arbitrary point here far away, then you have to take the component of this oscillation, that is the component of the y axis, in the direction perpendicular to the line of sight. So, you have to take the component perpendicular to this, and this is the direction of the electric field which is shown over here. So, the electric field is going to oscillate perpendicular to the direction of line of sight. So, it is going to oscillate in this direction. The wave is going to propagate along the line of sight. So, which is the direction k, this is the wave vector. It points from the dipole to the point where I am calculating the electric field. So, the wave is going to propagate in this direction and the electric field is going to oscillate in this direction. Its magnitude is going to be smaller than the magnitude of the electric field here, and this is going to be smaller by a factor of sin theta, where theta is the angle between this direction and the dipole. And if I look in this direction, theta is going to go to 0. So, sin theta becomes 0, there will be no electric field produced by the dipole oscillator in this direction. So, for any other direction other than this dipole oscillator far away is going to produce a sinusoidal plane wave. The magnitude of that the magnitude of that sinusoidal plane wave is going to fall as sin theta. Now, next let us calculate the magnetic field. The expression for the magnetic field is given over here. You have to take the unit vector along the line of sight to the dipole and do a cross product with the electric field, divide by c, and there is a minus sign here. So, in the problem which we are dealing with, this is the point. Let us again go back to the x axis. The line of sight is along the minus x axis. So, the E cap vector is minus I. So, the E cap vector is minus I, and the electric field is along the y axis. So, it is along j. The magnetic field is going to be minus E cap, which is I cross E by C. So, the magnetic field is E by C, the magnitude of the magnetic field is E by C. It is in the same phase. So, it has cos omega t minus k x, and it is in the z direction. I cross j is the unit vector k. So, it is in the z direction. So, going back to our picture, along the x axis, the electric field is going to oscillate in the same direction as the dipole, which is along the y axis, and the magnetic field is going to be perpendicular to both the direction of the propagation of the wave and the electric field. The magnetic field is going to be along the z axis. So, this is a typical feature of electromagnetic waves. In electromagnetic waves, the wave propagates in a particular direction, the electric field is perpendicular to that, and the magnetic field is perpendicular to both the direction of propagation and the electric field. The oscillations of the electric field and the magnetic field are both in exactly the same phase. The magnitude of the magnetic field is a factor 1 by c smaller than the magnitude of the electric field. So, this is a feature which is typical of all electromagnetic waves. So, in this part, in the previous lecture and this part of the lecture, we started off with the laws which govern the electric field and magnetic field produced by a charge, and I showed you that there is a term which falls as 1 by r. This term arises only when there is an accelerating charge, and if I have a sinusoidally accelerating charge or a dipole which is oscillating, it then I showed you that such a thing produces a sinusoidal plane wave, an electromagnetic wave at large distances, and this electromagnetic wave has a direction of propagation. The electric field is perpendicular to that, the magnetic field is perpendicular to both the electric field and the direction of propagation, and it is in phase with the electric field. This is very generic feature of electromagnetic radiation, and I also showed you how such electromagnetic radiation can be produced, how it can be generated using dipole oscillators. Let us now move ahead. So, let us calculate the energy density in this electromagnetic radiation. Now, all of you must have already learnt that there is some energy in electric and magnetic field configuration, and the energy in the electric field configuration is half epsilon naught E square. The energy in the magnetic field configuration is half B square by mu naught. So, let us now calculate the energy density, that is the energy density. So, let us now calculate the energy density in this electromagnetic wave produced by the oscillating dipole. So, this is the expression for the energy density, as I just told you, which I am sure is familiar to all of us, and for the electromagnetic wave we saw that the electric and magnetic field are not independent, they are both produced by the same source, and the magnetic field, the magnitude of the magnetic field is the magnitude of the electric field divided by c. So, I can replace the term arising from the magnetic field and write it in terms of the electric field as 1 by 2 c square mu naught square into E square. We also know that the constants epsilon naught and mu naught are related to c square, they are not independent, they are related to c square, and c square is 1 by epsilon naught into mu naught. So, using this expression, we can write the expression for the energy density in terms of the electric field as epsilon naught E square. The two terms turn out to be exactly equal. The electric field and the magnetic field, it turns out, contribute the same amount to the energy density, and the energy density is epsilon naught E square. So, let us just go back to the situation. We have an oscillating dipole, or we have a charge going up and down at an angular frequency omega. This produces an electric field far away, which also does oscillations at exactly the same angular frequency. So, the electric field is also oscillating at an angular frequency omega. Now, the instantaneous energy density in the electric and magnetic field, the magnetic field is also oscillating at the same frequency. So, the instantaneous energy in the energy density in this electromagnetic field, we just calculated that it is epsilon naught into E square. So, if the electric field oscillates with angular frequency omega, the energy density depends on E square. So, we have already seen right in the first lecture that the energy density is going to also oscillate, the instantaneous energy density is also going to oscillate, and it is going to oscillate at twice the angular frequency of the electric field. So, the instantaneous energy density, that is what we have calculated here, is going to oscillate at twice the angular frequency at which the electric field is oscillating. Now, the quantity of interest is not the instantaneous. In most situations, the quantity of interest is not the instantaneous energy density, but the time average energy density. In most situations, the electromagnetic field oscillates quite fast, and the quantity that we measure is not the oscillating energy density, but the time averaged energy density. For example, the bulb which illuminates the room is is emitting radiation. This radiation is oscillating at a frequency. The value of that frequency we shall discuss after 1 or 2 lectures, but it is an oscillating, as we have seen, the electromagnetic radiation is an oscillating electric field. So, the value of the electric field is oscillating, but we see a steady illumination. That is because our eye and most optical devices measure only the time average energy density. They record the energy over a time period which is much faster than the time at the rate at which the electric field is oscillating. So, they only measure the time averaged energy density. So, we wish to calculate this quantity which is of practical interest. So, to calculate this, we express the electric field in the complex notation, as you can see here, and then the time averaged energy density is the time average of E square, which in the complex notation is E into E star by 2. So, this gives us the average energy density. It is half epsilon naught E square, where E is the magnitude of the oscillating electric field. This is the expression for the average energy density in an electromagnetic radiation. Now, remember that we have energy in the electromagnetic field, but the electromagnetic field pattern is a sinusoidal plane wave. The sinusoidal plane wave is propagating forward, in this case along the x axis. We were discussing waves along the x axis. So, the sinusoidal plane wave is propagating forward along the x axis, and it is propagating forward at a speed c. So, the energy density in this electromagnetic field does not remain fixed over here. The whole thing propagates forward at a speed c, the speed of light. So, let us now ask the question. We take a surface perpendicular to the direction in which the wave is propagating. So, in this case, the wave is propagating along the x axis. So, we take a surface perpendicular to the x axis and ask the question, how much energy crosses this surface, crosses a unit area of this surface per second. So, what is the energy density? By energy density, we mean the energy flux. So, this is what we call energy flux. The energy flux is the energy which crosses per unit area of the surface in a unit time, and this is the energy density into c, because the whole thing is moving forward at a speed c. So, if you take a unit area and ask the question how much energy will cross it in a second, the amount of energy that will cross it in a second is the energy density into the speed at which it is moving, which is c. So, this gives us the energy flux. Let me just elaborate a little on this. So, energy flux is the energy per unit area per time per unit second, and this is the quantity which is of considerable practical importance, because whenever we have a detector, for example, we have a detector of some sort which is measuring radiation, the quantity that we detect is the amount of radiation, energy per unit area. So, we have the area of the detector. If I double the area of the detector, I will get twice the radiation energy. So, the amount of energy per unit area of the detector per second, and this has a unit of so energy per unit time is power. This is also, you can think of it as power, which crosses per unit area, and this has got units of joules per meter square per second, or you can also say that it has got units of watt per meter square. The power which crosses per unit area, the power of the radiation, the power from the radiation per unit area, and this is the energy density into C. So, calculating this energy density into C, we have half epsilon naught into C into E square, which gives us the energy flux. You should also remember that the energy flux is a vector. It is a vector in the direction. So, this energy is moving in the direction in which the wave is propagating. So, it is a vector, and if I were to calculate it at some other point, the energy would be moving in some other direction. So, along the x axis, the energy is flowing along the x axis, it is the energy density into C. If I were to calculate the energy flux here, it would be a vector along this direction, along the direction of the wave, and it would be the energy density here into C. It would be in this direction. So, in the next, let me stop here for today. In the next class, we shall calculate this expression for the flux and go ahead further from there.